Cast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Welcome to the Golden Gate chapter webinar on passives in the FDX environment. I'm excited to have Neil Tang doing a presentation. He's going to tell us all about passives because that's one thing that gets forgotten when we do upgrades, and some of the things that go wrong when we don't pay attention to the passive. So Neil's going to address that and talk to us about what a passive role is, and what happens when we put a lot more bandwidth in different directions in the through the passive. With that, I just wanted to also promote an upcoming all California chapters training summit. I'm sorry, mine's a little slow this morning, but training summit, and that'll be on the first week of December. We'll have 4 straight days of training in the morning, so we have a wide range of topics to choose from. So check that out. You'll see that on our website, and you probably have received email announcements, but we have a little bit of something for everything. And I just like to promote the benefits of membership. So if you're not a member already, you seriously may want to consider. Again, these webinars are recorded. We have those available to play back later in case you missed part of it, or you have somebody that wants to attend. That's one of the benefits, and we have many more. So check out members benefits on scte.org, and you will be impressed. For those that are in the All Cable Labs member program, and Comcast is one, I think Charter is too, you can just go in and sign up, and then it just automatically renews forever. So very easy to do, and if you need help, certainly reach out. We'll get you signed up. With that, here's Neil. Thank you, Neil.
Thanks for the introduction, Woody, and great to be here to part of this training. And I think SCT is doing a wonderful thing, providing guidance and training on all different topics. So today is passives. I'm Neil Tang, President and CTO of Antronix, and we typically are all things passives at Antronix, and like to go over some of the products and details of how that affects the network, especially in FDX systems. Let me make sure I'm sharing my screen. You see my slideshow? Or is it me?
I can see your slideshow, yes, sir.
Okay, great. Okay. So here's the agenda for today. We're first going to talk a little bit about the bandwidth needs in the network, a little bit on the FDX overview for full duplex DOCSIS, and the passes that are actually typical passes that are actually used in the network, and the RF parameters in the passes. You have to understand a little bit about the RF parameters in the passes to see how those parameters affect full duplex DOCSIS. And there are some other considerations when dealing with passes for full duplex DOCSIS. We'll talk a little bit about those as well as some tap plug-in conditioning concepts that the system can use to optimize your network as well. So the largest asset for the cable MSO is, of course, the HFC network. They have over 88% of the coaxial cable penetration in the United States. So 88% of the homes passed can be serviced with high-speed internet to the home. And most cable operators have the desire to use the existing infrastructure with least interruption. So as you do this, you get fiber deeper into the network, but you use the existing coaxial plant for the last leg to the home. And that's the most costly to deploy, digging fiber. But if you have coax there already, the asset that cable operators have, they want to use that asset to the full life of the coax. So as you increase the bandwidth, there are a few possible solutions that people implement now. So currently people do node splits. You can do that to a certain point. Head-end space is limited, power and cooling is limited. You can do node splits up to a certain amount to increase upstream. People have upgraded their diplex filtering. You have 5 to 42 upstream, can give you about 100 megabits per second upstream. As you go to mid split and high split, that does increase your upstream a significant amount. But while you do that, as you increase the upstream spectrum, you actually take it away from the downstream spectrum. So that has a solution where the industries develop DOCSIS 4.0, the next generation of DOCSIS. This specification was finalized by SCTE a few years ago, and products are being developed right now. And part of DOCSIS 4.0, there's 2 different standards. One standard is the extended spectrum DOCSIS, which is a frequency division duplex using same diplex frequencies, the same diplexers that's used now, but you're extending the bandwidth out to about 1.8 gigahertz. In this scenario, passives must be upgraded. But the focus on this presentation is more on full duplex DOCSIS. Full duplex allows simultaneous upstream and downstream on the same frequency. This is very different than what cable is used to. You're used to the upstream frequency band and the downstream frequency band. The lower frequencies is the upstream, the higher frequencies are the downstreams, and diplex filters in there separate, diplex filters in your network separate the upstream and downstream. In full duplex DOCSIS, you're allowed the same frequency to have both upstream and downstream communications. So in this scenario, we don't have to go up to 1.8, and passive upgrades are not required. They can be, but it is not required to go up to use full duplex DOCSIS. Here's the current typical diplex band splits in today's full FD networks. You have the subsplit that's currently used in the majority of systems now. Many cable operators have upgraded already to mid-split in their networks, and others are going to high split. But as you can see, as you increase the upstream band, going from 42 megahertz or to 85 megahertz to 204 megahertz, you're actually taking away from the downstream bandwidth. Your downstream bandwidth is actually being reduced when you go up to the higher upstream. So here comes DOCSIS 4.0 and the full duplex solution. Full duplex actually allows a certain frequency band, and currently the target is 108 megahertz to 684. And in that band, you can actually simultaneously transmit upstream and downstream within those frequency bands. So still the lower frequency band from 5 to 684 is all upstream, but there's an overlap from 108 to 1218. Now that part's downstream. This allows roughly 10 gigabits of data downstream, and up to almost 6 gigabits upstream is possible, which provides 10 to 50 times more upstream bandwidth than what we're used to today. So full duplex DOCSIS, this is the band 108 to 684 that has transmission at the same time, upstream and downstream. So simultaneous transmission. No diplex filters are required to separate the upstream and downstream signals. And the great thing is the upstream and downstream bandwidth and speeds can be scaled dynamically for ultimate flexibility. So if you need more upstream or need more downstream for a particular event that's going on or particular service customer, that can be scaled dynamically to satisfy those needs. But to really understand the impact of how passives affect FDX, you really need to understand the parameters in a passive. So there are some RF parameters in a passive we're going to discuss a little bit. So here are some typical hardline passives in a network. Here's a typical network here. You have the power supply. You have a power inserter that injects AC in the RF network. You have line splitters that split signals equally. You have directional couplers, unequal splits. And we're going to talk a little bit more in detail about taps. These are taps in cascade that taps off the signals to 2, 4, or 8 ohms. Here's a 2-way tap going to 2 ohms, 4-way tap here in 4 ohms. I didn't show an 8-way tap, there's just too many icons for ohms there. So, and also there's taps that have AC power on the F port to power access points. And you also have cable equalizers, equalize the cable slope in a network. So to really understand it, we're going to first talk a little bit about insertion loss and return loss. So on a tap, you have the input power and the output power of a tap. What comes in doesn't necessarily what comes out. There is an insertion loss through the tap. A tap has some insertion loss associated with it. So let's say if you have a 40 dBmV signal going in and a 39 dBmV signal coming out, you get about 1 dB insertion loss through the tap. So that is the actual passive loss going through a tap. Now, insertion loss varies with frequency. So at each frequency, you may have different insertion losses. As we move on to return loss, in an ideal system, everything cable TV is a 75 ohm system. This tap is designed to be 75 ohms, but not everything is ideal. So in a real 75 ohm system, there's power in is equal to power out. So there is no loss, but that's never the case. It's never exactly 75 ohms. So whenever there is some impedance mismatch, that means there's not an exact 75 ohms, there is some power reflected. And this power reflected, what goes into the tap, some of that's actually reflected back and going back the other direction. And this is indicated by the return loss of the tap. So the return loss, the better. Less reflected power. As you can see in a typical product, you may have a good return loss of about 20 dB. 20 dB return loss translate to 99% of the power is being transmitted through, and only 1% is being reflected. So if you have a 20 dB return loss, most of the power is going through the product, and you have about 1% reflection. But if you have a return loss, let's say 5 dB return loss, and these return losses are usually all specified on the specification sheets by the manufacturer, you're getting 31.6% of the power being reflected back. So return loss is a key requirement and specification when you're dealing with FDX. We'll go into that into a little bit more details. So every interconnect, if you have an F connector, if you have a passive, any interface has a return loss specification to it. And that means that there is some degree of reflection, no matter how perfect that product is, there is still going to be some reflection going back. And depending on the degree of reflection, that will impact how FDX works in your network. To further illustrate the example here, you could see a tap, let's say it has about 20 dB input return loss. So has a decent input return loss there. If you have an input power going into the tap of about 35 dBmV incident to the input port of the tap, at 20 dB you get a reflected power, and that reflected power in red is a signal going back towards the node, and going opposite direction. So in that case, a 20 dB return loss, so you subtract 20 dB from 35, you get about 15 dBmV of reflected power going in the opposite direction. And that's kind of important to understand how return loss affects how FDX operates. And we'll go into that in a little more detail.
Neil, can I just make a couple of observations?
Sure.
Yeah. And we talked about insertion loss of taps, and I go way back when we had limited bandwidth in the downstream. So insertion loss was, we called it flat loss. It was never really flat loss, but it was close, right? And when you get now we're pushing, frequencies above 1 gigahertz all the way up to like 1794. Yeah, it's anything but flat when you're crossing that much bandwidth. So folks need to keep that in mind. Is not only does cable introduce slope, but every device in the network will produce some slope. I don't know if it follows the same rule as coax, but coax rule was every time you quadruple the frequency, you would double the loss.
Correct.
And I don't know if passives are that same calculation or not, but it's significant. And the second thing, for those who may not be aware, return loss, the higher the better. So if you're looking at that number, you want a higher number. So also consider return loss when you're testing the network with the TDR. It's good to know about what a TAP's return loss is, because if you're testing a coax passive run with the TDR, and you see that return loss fairly low compared to what you would expect, that's an indication that you may have a faulty passive. Okay, I'll be quiet.
Yep, that's great, because coax, as a signal is transmitted down coax, the insertion loss is different at different frequencies, like what Woody mentioned. And lower frequencies have less insertion loss, and as it travels down the coax, you get more insertion loss at higher frequencies. I did not include that in this presentation, but I do have some plots and charts where it shows how a signal going down the path may be flat at low frequency bands, but then as it travels down the coax a fairly longer length, you could see the response of the whole curve have a downward slope, meaning the higher frequencies has more loss and it transmits further, and that accentuates more when you have higher frequencies. So you're going out to 550 or 750 or 1.2, you'll get more insertion loss there, and that has a slightly large curve. And that is more so when you go to 1.8. If people do extended spectrum and have passes going into 1.8 gigahertz, you get even more insertion loss associated with that as well. So going off a little bit more details on what a tap is before we talk about the impacts of this. A tap is typically used just to tap off the main line. You have the input and output here, and typically they come in 2, 4, or 8 port taps with various dB values. And this dB value is the loss between the hardline input and the drop connection at the F port. So here's the basic block diagram of a tap. You get the AC going in and out from through the hard line. And the first block diagram is a directional coupler. This is a symbol for a directional coupler. You have an input and output in the tap. So depending what the value of the directional coupler, it taps off the signal off the main line, so to go down to the F port. So you have a lower loss port, which is the going through line, more signal, and the tap port has a lower signal to tap down to go to the F ports. And there's also a splitter after that. In this case, it's a two-way splitter for a 2-port tap. It equally splits the signal, an equal power divider. A 4-port tap would obviously have 2 more splitters after that, and an 8-port tap would have another set of splitters after each of those outputs is split at 8 ways. So that's basically the basic block diagram of the tap. So the goal for a tap is to design the system so you have the same signal level going to each home of subscriber in the network, regardless of distance that passive is from the node or the amp. So what is needed is taps have different dB values, and those dB values is the loss values through the taps. So the signal levels are attenuated through the tap as they travel on the coax, but the taps are attenuating the signal so that each home has the same signal level. So for the purpose of this discussion, we're not going to talk about the slope across the coax of the tap. So we're going to assume flat loss, which is not the case, but we're going to assume flat loss on coax. So if you have an amp that has an output level of plus 40 dBmV, it goes down the coax to the first tap. Let's say the goal is to have 12 dBmV at each home. At the beginning of the tap, you get 5 dB of coax attenuation loss. At 35 dBmV at the input of the tap, to get 12 dBmV at each home, you will need a 23 value tap. So 35 dBmV at the input, you subtract the 23 dB of signal level, so at the home you get 12 dB. And that's why there are different tap values going down a cascade. You attenuate, the signal goes down further to the next tap. Let's say it attenuates another 3 dB from here. Then to get 12 dBmV, you would put a 20 dB tap. And so on and so forth down the line. And that's why you get various tap values in the cascade, from a higher value tap towards closer to the amp and node, and a lower value tap towards the end of the cascade. And the purpose of that is trying to maintain the same signal level at the home across the whole cascade. A typical insertion loss through the tap, as you can see here, is a sloped line coming down. As you can see, as the higher frequency we mentioned before, the higher the frequency, the more the insertion loss. So you want a lower insertion loss, the better. On a 23 dB tap, it is designed to have 23 dB loss. So that is the signal going from the input to the tap ports. And across the band, ideally, it's going to be exactly 23 dB, but it does vary over frequency. The scale is kind of large here, but if you zoom in, you'll be able to see it's gonna not exactly 23. It'll be 23.2, 28, 22.8. It'll vary across frequency. A key parameter is also isolation, and there's two different types of isolations. So a tap is designed with a directional coupler. So when you go from in to the tap port, you're getting a fixed value, which is as shown here in the tap loss. So the directional coupler shows a 23 dB fixed loss through the tap. But when you go in the opposite direction, so this signals from the downstream cascade going upstream. So if it's going in this direction, you want that signal to go directly to the node, not down the F port to another house. So you want a high isolation. So isolation is actually the measure of insertion loss, but we typically say isolation, you want high isolation, so high insertion loss going from the out to the tap. You don't want the upstream signal of a home that's downstream to affect another home connected on a tap right before it. So as you can see, a plot, you want high isolation. That means there's more loss through the tap going in the upstream direction and not affecting your signal. Same thing with tap-to-tap isolation. So you can have two homes connected to two different F ports on a tap. You want the two homes to be isolated. So you want a lot of loss. So if I have a modem transmitting at one level at one home, at one F port, you don't want that signal to go down the other F port. So the measurement of isolation from tap to tap ensures, well, is a measure of how well the two homes are isolated. So you want a high number for the isolation so that the signals will not go from one side to the other. They will, but it will be attenuated by this amount. And as you can see, different frequencies are attenuated at different amounts. So you can see here, you know, in the 800 megahertz range or 600 megahertz range, it could be about 28 dB of isolation. But in the 100 megahertz range, it could be around 38 dB of isolation. So depending on when what frequency you're transmitting, the isolation is also different across the bands.
I would like to comment on that if I may. With DOCSIS 4.0, the port-to-port isolation becomes very important. The modems are going to be transmitting, you know, hundreds of megahertz wide bandwidth of power. And so the probability that one could potentially interfere with the neighbor becomes quite high. So port isolation is very important
Yes.
going forward. And the other thing is that with DOCSIS 4.0, we go to a single outlet. We don't have multiple outlets. We don't have the benefit of splitters and other things creating loss. So we have to pay attention to how much power is coming back through that drop. And again, try to prevent that getting into the neighbor's feed so they don't have issues with overloading the front end of their device.
Correct. And the last parameter I'm going to talk about a little bit too is return loss. We touched about it in the prior slides. This is the return loss. You have an input. There's 3 different return losses associated with taps. You have the input port, the output port, and the tap port itself. So you want a high return loss. In other words, this is a measurement of S11 or S22. This is the dB value of the loss. We talked about 20 dBs in this line here, but as you can see at different frequencies, you get different return losses over here. And this is the input return loss of how much it attenuates the signal when it was reflected back in dBs. Same thing with output return loss and tap loss. So as we talk about those parameters, we're gonna go into how full duplex DOCSIS works and why these parameters are important in a full duplex situation where you're transmitting at the same frequencies as you're receiving at. So in a typical cascade here, you have taps, and I showed 2 port taps for 2 homes for simplicity's sakes, and you have a node. Let's go down into a little deeper into the cable modem for a full duplex DOCSIS cable modem. So within one of these homes, how full duplex DOCSIS FDX works is the key feature is the echo cancellation that is occurring in a cable modem. So because you're transmitting and receiving at the same time at the same frequency, what the echo canceller does is the cable modem knows what I'm transmitting. And what it does is it creates 180-degree phase to cancel out any reflection that's coming back. So any upstream signal, I am using, because I know when I'm transmitting upstream, I can detect that same signal coming down as a reflection. We talked about any interface may have a poor return loss or a non-perfect return loss. So as the upstream is transmitting going up the tap, some of it's going to be reflected down. And because the cable modem itself knows what it's transmitting, it's able to create a negative 180 degrees phase shift. You add the 2 together to effectively cancel as much as you can of the upstream signal. So how I like to say it is like when I'm screaming and I'm yelling at a person and they're whispering to me because I'm trying to listen at the same exact time on a downstream signal from the node at the same time I'm transmitting very at a high output. So if I'm screaming at somebody and somebody's whispering to me, it's very hard for me to hear them. So this echo canceller actually using signal processing to create an image of what I'm transmitting, invert that, and do a cancellation, like a noise canceling headphones. It is canceling the reflected upstream signal in that cable modem. That's the main, one of the key highlights that allows full duplex to operate. So the cable modem requires a DOCSIS 4.0 FDX modem. The same thing applies at the node. The node has an echo canceller as well. So signals that are transmitted down a line, that's reflected back because the node knows when I'm transmitting downstream. Any reflection on the lines coming back, I'm able to create an image and subtract that from the reflected signal, the downstream signal, subtract the reflected signal coming back. So the echo cancellation is the key block diagram that allows full duplex to operate and cancel out those echoes. And that's why return loss is a key parameter. So here's a scenario, full duplex DOCSIS scenario 1 here. You have an FDX node, and it is transmitting at a very high signal level. So the total composite power could be greater than 70 dBmV, a very, very high level. And if I have a tap that's very close to this FDX node, some of that signal will be reflected back. Now, any physical interface has imperfect and return loss. Nothing's ideal. So because of the high transmit level, even if I have 20 dB, 30 dB return loss, a lot of that signal is going to be reflected back into the echo canceller at the FDX node. So it is important that high value taps have good input return loss, because that is where the FDX node will have higher signal levels and more reflection will be coming back. In scenario 2, we'll talk a little bit about lower value taps. And the problem with lower value taps, we'll illustrate here. Let's say you have home 1. You have a transmit power of, let's say, plus 40 dBmV. As that modem transmit upstream, you get a desired, we have a downstream signal from the node of about plus 10 dBmV. So these are the signals that it's transmitting, signals that it's receiving. So it's transmitting much higher level than the received signal over here. But as this transmit signal goes up to the F port, some of that is reflected back at the F port, and that's due to the return loss or any kind of F connector, or if there's any imperfections in the coax cable, squirrel chews, etc., that could cause a reflection coming back. So the echo canceller within that home, because I know I'm transmitting and that same signal is being reflected back, it's able to do some degree of echo cancellation and remove that and really detect the received signal, even though I'm having such a high reflected signal coming back. But the problem would be in the home number 2. So this home number 2 is still transmitting at 40 dBmV, and this is what's supposed to be going back to the node. But the parameter of isolation that we talked about in the tap, you want high isolation between the 2 ports. But some of that signal is actually going to go down the drop to the other cable modem, to the other home number 1 here. Because taps may have an isolation, let's say of 20 dB, that means your signal going down 40 dBmV transit level, isolation of 20 dB, you get a plus 20 dBmV signal level coming from the adjacent home going to home number 1. Your desired signal here already is plus 10 dBmV. Your interference signal is already higher than that. And what FDX doesn't do, what echo cancellation cannot do, is to cancel, because I'm transmitting on this home, I know what I'm transmitting, so I can echo cancel that. But this modem does not know what this modem's transmitting it, so I cannot echo cancel this cable modem on this adjacent home for the tap. So high isolation between the F ports is key, and that was something that Woody mentioned earlier. You do want products with high isolation to prevent an adjacent home from interfering the cable modem. So echo canceling, good at canceling self-interference, but it cannot cancel interference from a nearby cable modem at an adjacent home. How does the network help resolve this concern? FDX creates interference groups. So what interference groups does is you have you create two different groups or multiple groups, and in this instance I've been showing two interference groups. So each modem will be transmitting and receiving at different time slots to enable this. When this modem is transmitting, this one is not transmitting at the same time at that same frequency. So home number one may be assigned an interference group number one. Home number two may be assigned interference group number two, because maybe these two are connected by that splitter that I talked about. So these two splitters, the splitter on these two ports is the same splitter, and that's limited by the isolation within that splitter. And if that isolation isn't high enough, then you got to create interference groups. And to do that, you create multiple interference groups. So you can assign different homes, different ports, different cable modems to different interference groups. Let's say these ports of these homes is interference group 1. These homes are interference group 2. Those have lower isolation between these two interference groups. So therefore, you're transmitting at a different time. And as you allow more interference groups, you're able to get all the signals to transmit and receive under full duplex at the CMTS view. But it slows the data rates a little bit, but you do get the full duplex features that you need. So the system is operating full duplex. The direction of the data transmission of each cable modem in an interference group is dynamically assigned by a resource block allocation. So they're sort of transmitting in a simplex mode, each cable modem, but the whole system is in full duplex. Any questions over there on full duplex?
I do see a question. From some folks that couldn't attend the training. Why do we see a noise spike at 46 megahertz on all FDX node? I'm not sure that's a question you can answer, Neil, but maybe you know.
46 megahertz on all FDX nodes.
So I presume they're looking like at a spectrum analysis and they see 46, a spike at 46 megahertz. My question for the persons asking the question would be, is that on an ATDMA signal or traditional upstream QAMs? Because I'm just thinking maybe that's the pilot that they're seeing, that they could be seeing on an ATDMA, but I'm just guessing. So sorry, whoever asked that question. I'm not sure. I'm not sure of that answer.
Maybe we could do the first poll right now. Is a good spot to do it.
Okay. Okay, audience. I'm going to launch this poll. So if you would please take a second and read it, and then answer it, and then we'll see what the results are. So when do you intend on deploying FDX in your network? So if you know that answer, yeah, please go ahead and answer. And we've got about 16% of folks that voted. It's climbing, so we'll give it a minute. We're up to 43%. So if the audience, if any more of you guys would like to answer that, we'll get this out so everybody can see where we landed. Well, we seem to hit a stop there at 56%. So let me close this and display the answers. So there we go. I don't know if you can see this, Neil. Maybe you can.
I don't see it. But...
Okay. It shows I'm sharing, so hopefully you do. So the answers were 40% answered, I am deploying now, 24% within the next year, and I have plans, but not sure when, 20%, and no plans to deploy, 16%. So we had a wide range of answers, but it looks like about half or a little bit more than half are deploying now or within the next year.
Interesting. Great. Okay, I will continue on. So for full duplex DOCSIS, your taps and passes should be a 1.2 gigahertz. You don't need to go out to beyond that, and full duplex can work across whatever, all the frequency bands, but it is currently designed and implemented in the 108 to 684 megahertz right now. And that could be expanded down the road. It could have a higher overlap in upstream and downstream transmission. So 1.2 gigs taps and passes are fine. There are 1.8 gig taps and passes from suppliers. Those taps and passes can be used in full duplex and extended spectrum. So even though you buy an extended spectrum 1.8 gig tap and passive, it can still be operated in a full duplex 1.2 gig network. Just want to make sure everybody's aware of that. There's some other considerations for FDX, and one of the key things is AC power interruptions. So as nodes are deployed with DOCSIS 4.0, they require remote PHY devices, RPDs, and they're basically mini computers inside the node. And when AC is actually interrupted to the RPD node, there could be a reboot. So the computer, the remote PHY device in the node needs a reboot, and it could be a 10 to 15 minute service interruption. So maintaining AC power on your network is very important. It depends on how the powering structure is in your network. So in taps have a make before break in the housing. So here's a drawing, a photo of a bypass that's inside. No stinger connectors, line connectors are connected here, but there's a bar that connects the input to the output. So when the faceplate is on, the signal goes through the faceplate, goes through the tap. But when you remove the faceplate, the signal is actually going through, is shorted from input to output. So ensuring that when the faceplate is pulled out of the tap, downstream, the downstream cascade has AC and RF continuously going down. So when faceplates are removed, the bypass makes a connection from the input to the output port. So, and you want to make before break. What do we mean by make before break? You want to make sure that there's no interruption before the the circuit is broken when you remove the faceplate. So you want to make the connection with the bypass before you break the connection with the faceplate removal. So this ensures, AC and RF downstream. And pretty much all taps that you buy now these days do have a bypass from all your vendors and suppliers. So when you remove the faceplate, you're getting good continuity of AC and RF downstream. And because this is a 2-port device for the hard line, to ensure that AC is just on the hard lines, not down the F ports.
I'm sorry, Neil, but there was a question I missed, and it goes back a few slides, so I apologize. But the question is the interference group put in place as a result of ingress?
Not a result of ingress. It is a result of, let me go back a couple slides. It is a result of the isolation between different set-top boxes. So different cable modems, if the isolation between them is too low, you're not going to be able to transmit and receive at the same frequency. So they create interference groups to ensure that the isolation between the cable modems is if the isolation is too low, you got to create interference groups so they don't transmit and receive at the same time. So it has nothing to do with ingress. It's dealing with the how isolated each cable modem. So what the FDX system does, it polls each modem to find out how well they interfere with each other, and the system dynamically assigns an interference group to each cable modem. And in this simple example, I just put 2. I'm assuming the ones in interference group 1, they have high enough of an isolation between these ports that they can operate in full duplex, because remember, each tap is separated by a splitter. This is a splitter, this connected by a splitter, but then this splitter is splitters and cascade together. So the interference groups are created to isolate the cable modem so they can transmit and receive at the same frequency at the same time. That does not have to do with ingress.
So to summarize, the interference groups is primary objective is to minimize interference of modems between each other. Ingress throws a whole new wrench into everything. So
yes.
You have ingress, and then I don't know how well any of this works, but it definitely will have an impact.
Correct.
There is some ingress limiting, where we can minimize the impact of interference, but keep in mind when you utilize those tools, that takes bandwidth, right? So, and just to plug our upcoming webinar on the first week of January, we're going to be talking a little bit about that, about how things like ingress affects your throughput, but not necessarily customer experience. So we'll get into that later, but thank you, Neil.
Yep. Okay, so we were mentioning taps and passives do have a bypass, so there's no AC interruption. And the key part is no AC interruption, so we don't have interruption to the AC that powers the node, which has an RPD, because it will cause a 15-minute, it could cause a timely reboot situation where that whole node will be out for a period of time. But line passives do not have a make-before mechanism. So these 2-way line splitters, 3-way line splitters, directional couplers, they do not have a make-before break. Most line passives has the hard line is connected to the housing, as you can see here, and the faceplate has the printed board assembly in there. So when you remove this, you're breaking connection. So the PCB printed circuit board assemblies in a removable faceplate, the advantages here is, it's a quick, faceplate replacement in case there's lightning strikes or any storm damage, you can just replace the faceplate. But the disadvantage is when you remove the faceplate, you are interrupting RF downstream and up, and all signals, AC and RF. You're just disconnecting everything. And depending on how the powering is, you could be powering a device that is connected to our RPD nodes on a line passive. So be careful when you remove a faceplate on a line passive out there, because it will interrupt AC and RF. But there are alternate line passives where the printed board assembly is in the housing. So if the printed circuit board assembly is in the housing, when you move the faceplate, it's just a blank faceplate here, and there's continuity of service going out here. But there's disadvantage of that is that the advantage of that is no AC interruption when you move the faceplate, but the disadvantage is that it looks like you resplice during failures. But there are passives, like our passives over here has a removable printed circuit board assembly. These are little pull tabs, and you can remove this whole faceplate. It's a press fit in, so you can remove that and not necessarily have to resplice on during storm damage or anything like that. So keep in mind when you have line passives, making sure that AC power is maybe interrupted when you move that faceplate, and it could affect your node power. Line passive. All right, here's another line passive. This is something to do, have to do with FDX as well. We mentioned that you do not need a diplex filter in FDX. In this example, I have a subsplit shown here. This is the frequency response of a diplexed inline equalizer. So we're talking about inline equalizers when cable when signal goes down a cable, it's in the opposite slope direction as this. This is the frequency response of the inline equalizer. So cable has a slope that's going down the way I'm drawing on my arrow here, opposite direction. So when you put the two together, it flattens out your signal. And when you have full duplex, you don't need a diplex filter, and you kind of want a full bandwidth equalizer. This way you can dynamically change, there's no diplexer in here, you can dynamically change whatever upstream and downstream frequencies, and this is the preferred method if you're allowed to accommodate, if your system's able to accommodate this 8 dB of, well, the way we have a few different versions, 8 dB, 12 dB of upstream loss. So the blue response is a full bandwidth equalizer. The red response is a diplex version. You typically do not want to use a diplex version in FDX environments.
I have a question, Neil, if I may.
Sure.
Do you find operators use both LEQs and equalized taps, or do they choose one or the other?
That's a great question. Ready for my next poll question? That's exactly my poll question. So, in summary, there are both, and you may want to put the next poll question up. Both.
Okay, give me a second. I'll get it up here. Okay, folks, I have the poll question up. So the poll question is, which is the preferred method for equalizing cable slope? So three possible answers: equalizers via tap conditioning, plugins, inline equalizers, or both. So I apologize. I forgot what the poll question was. I didn't mean to bring that up, but since we're here, we'll go ahead and answer it.
In our experience, we have cable operators using both. So, and a lot of them use plug-in conditioning. A lot of them use equalization, inline equalizers. And where in the past people have using more diplexed versions, more and more people are migrating to the full bandwidth version, because as you upgrade or change your upstream diplex, as people go from sub-split 5 to 42, or mid-split 5 to 85, or to high split, if they have a diplex version, they got to go revisit that equalizer, inline equalizer location, and switch that out.
So we have about 35% folks have voted in the poll. So we'll give it just a little bit longer. I don't see it moving, but just a warning for those folks that have the diplexed inline EQs. Those will have to be removed in order for FDX to work, or replaced, removed or replaced. And depending on the system design, that will take just replacing the device and or re-equalizing the taps to offset the effect of removing the equalizer.
And if you have a diplex equalizer already in your network and you're going to FDX, most vendors do have a blank plate, just like a bypass splice block plate. You can remove that equalizer and put in a blank plate there where there's no equalization, or replace that with a full bandwidth equalizer. So if you're planning on doing tap equalization, you can put a blank plate in there, and it's just a bypass plate in that tap housing, in that line passive housing, and utilize tap conditioning or inline equalizing.
So it looks like the voting slowed down. I'm going to go ahead and display for the audience the results. So equalizers via tap conditioning plugins, 22% or 22% selected that answer. Inline equalizer, 17%, but a resounding 61% said we would be using both. So sounds like a lot of folks are using both.
Right.
Okay, I'll go ahead and close this and we'll move on. Thank you, everybody, for taking time to vote. And thank you, Travis Clifton, for taking time to ask a question. Anybody else would like to ask a question, please put it in the questions box and I will try to get it in a timely manner.
So I'm going to chat a little bit about tap conditioning as well. We just talked about inline conditioning. I'm going to talk a little bit about tap conditioning as well. And here's a standard block diagram of a normal tap. And you have that in-out, a directional coupler here, a two-way splitter for a two-way tap. And the tap conditioning is actually a plug-in filter that is placed between the directional coupler and before the splitter. So what does that filter do? You know, this conditioning, whatever filter you put here, it has no impact on the insertion loss. So because it's after the directional coupler. So the good thing about it, it affects just the drop. And it only impacts the tap ports, so down the drop. And as depicted, one plug-in conditioning is conditioning all the tap ports in that drop. You can't just condition one tap port down that F port. And when you plug in one conditioner, if it's a 2-port tap, 4-port tap, or 8-port tap, all 2, 4, 8 ports are conditioned by that filter that's in there.
So I'm sorry, I have another question. So does the plug-in conditioner have any impact on port-to-port isolation?
It could. It could. So depending on what type of filter you have here, so this is a two-way splitter. It's minimal. It's minimal, but it could have some minor impact. And as you can see, this is a two-way splitter here. And you want port-to-port isolation over here. Now, this is terminated, and making sure, one thing you want to make sure, any unused ports, you always put a 75 ohm terminator. That's a golden rule that everybody should follow. So you are terminating that with 75 ohms. So normally you have a jumper here. And when you want tap-to-tap isolation, every port should see 75 ohms. So a tap is shipped with a jumper, and you're terminated by the 75 ohm in your network. When you put in a different type of conditioner, depending on the frequency response, these conditioners all have good return loss. So these good return loss will make sure it has minimal impact. But like I said, not all conditioners are ideal and perfect. Not all, there's no perfect interface. So there's always going to be some return loss reflection and some return loss impact that will affect your isolation a little bit. But you should be having minimal impact.
And would you say putting 75 ohm terminators on the unused tap ports becomes even more important now with FDX?
Yes, it is important, particularly on unused tap ports, yes. And really important on lower value taps where the isolation, we talked about isolation. You know, high value taps have a lot of attenuation over here that helps terminate it, but you do want to put terminators on all unused ports, especially as you go to DOCSIS 4.0, and it applies for FDX and extended spectrum as well.
I could see having a lot more energy that's going to do something if you don't take care of it. So putting that 75 ohm port will definitely help with terminating that port with a 75 ohm terminator will definitely help deal with the excess energy that might be floating around causing additional interference.
Yes. So there's various different types of conditioners that you could plug in there. Every tap is shipped pre-installed with a jumper, so it just as if this was not even here, it's just connected in now. There's a cable equalizer, which has, and this is attenuation, so it has an upward slope that is a shape equal and opposite of cable. So cable has a downward slope like that. When you add the two together, it's a flat line. So cable equalizer is typically used on lower value taps towards the end of the cascade. Cable simulator is another type of plugin, which is exactly what it sounds like. It simulates the frequency response of cable, though cable has lower loss in the lower frequency bands, and the higher frequency on the x-axis, higher frequency, there's more loss. So these are typically used on higher value taps, closer to the node or amp. There's also diplex versions where you have a return path attenuator. There's a step diplex, flat response in the return band and pass band, and a high tap filter here with a minimal loss in our upstream, but attenuating the downstream. But, you know, like we mentioned before, we do not want to use diplexers in an FDX situation. We do not recommend a diplex version because you can accommodate the same thing with a full slope. So you can see a return path attenuator has higher attenuation in a low frequency band and lower attenuation. It's very similar to the cable equalizer, except it's more a linear straight line, and it's better matches for the cable as well. So we do not recommend the two diplex versions in here, but I've showed them just to let you know that they are out there, and you do want to prevent using them, especially in an FDX scenario. How these plug-in conditionings work, you know, you have a cable simulator, so they're typically, like I mentioned, used in high tap values at the beginning of the cascade. I'm exaggerating here. Let's say this is a 32 value tap. Nobody uses 32 anymore, but just for showing the purpose of how these plugins work, you know, this modem could be transmitting very, very high signal level to overcome the tap loss of 32 dB to hit the node at the correct proper level. So you have what we call, you know, loud talker, high screaming modems that is transmitting at the, you know, upper rail of that modem. So, and this is before conditioning, and simply putting a conditioning in. So here you have a 32 value tap. Instead of that, we're putting a 23 value tap, but putting a cable simulator 9 dB. So in the high frequencies, it looks like a 23 plus 9. It looks like a 32 value tap like previously, but in the upstream, it looks like a 23 value tap. So you get the cable modem transmitting at a lower level, at a sweet spot, yet getting the downstream signal levels that you wanted of 32 dB in this example. But, you know, like I said, nobody uses 32 anymore. but I exaggerated just to let you guys see what that does. So that's some of the functionality of the cable cylinder. Same thing with a cable equalizer. This is before conditioning. Cable equalizers are used towards the end of the line, and as the signal goes down the cascade, like I mentioned, you have a downward slope of that signal because higher frequencies have more loss, so the signal's attenuated down. And the modems at the end of the line are typically transmitting at a lower level because coax have less loss in the low frequency band upstream. The modem only needs to overcome 8 dB on the lower value taps. So low attenuation on the tap value, lower loss through the coax. Even though it's longer coax, it's lower frequencies. So the modem may be transmitting lower. So what a cable equalizer does is it puts attenuation in the upstream. So you have 10 dB of equalizer. Let's put a cable equalizer, 10 dB. It makes this previous downward slope into a more flat slope. When I'm attenuating the upstream by 10 dB, the modem is transmitting 10 dB higher. So you're doing a couple things here. You're getting a better carrier noise. The cable equalizer actually attenuates the upstream, which is what? Ingress. We talked about ingress. Ingress happens more on low value taps because it only attenuates ingress by 8 dB. But if you put a 10 dB cable equalizer, it does a double duty here and attenuates your ingress by 10 dB as well. So that funneling effect from all the noise within this home on low value taps is improved by using a cable equalizer and low value tap. So it does two things at once, and which is great. So looking at a typical design, we're going to show modems with low talkers, how to cure them, and how we provide better tilt at that tap, and also improve better signal noise. So when you have a whole network or a node, this is a typical distribution of your upstream transmit power in each modem. You could have some low talkers, low transmit levels, and you can have a few modems in the high transmit level. But most of the modems will operate in a sweet spot, but you have these high and low transmit level modems in a certain network. In the example here, we're doing an 860 system, 18 over 10 dBmV power levels, and in this scenario, your transmit level across the modems at this home, ranges from a 41 dBmV at the 24 tap to a 30 dBmV transmit level at 8 tap. So we're talking about an 11 dB range without any plug-in conditioning of transmit levels down one cascade leg due to the different tap values and maintaining the same signal level going to each home. So you're getting a high variation there. Making two adjustments, just two simple adjustments at the end of the line, and putting two cable equalizers here. If I put a cable equalizer 4 on the second to last tap and a cable equalizer 10 on the last tap here, you're increasing the cable modem signal level by 4 dB here, 10 dB here, to a sweet spot of 40 dBmV transmit level. So now my variation from upstream to downstream, from high transmit level to the lowest transmit level is only 4 dB. So you're narrowing that optimal modem transmit level, and these are tools that are used to be able to optimize your system. In this case, we're talking about reducing ingress as well, because we're reducing ingress by 10 dB on this port, assuming ingress is all in the low frequency band, which is usually the case when it's coming from in the home, and attenuates the ingress by 4 dB on this home. But one of the things with tap conditioning, they are designed in. They're not used as a tech troubleshooting tool. They are designed in, and make sure you follow the design and ensure you use the right plugins in your network, and that will give you the best optimal performance.
Neil, if I may comment, I remember Tech
Yeah.
saying, well, I used to find most of my ingress at low value taps.
Yes.
And that was true. So please take note, if you're getting ingress from a low value tap, you probably want to just pull that faceplate and make sure the correct equalizer is in place. Whatever the
Correct.
design calls for. And if you're pre-equalizer design, you may want to just calculate it yourself and put one in, whatever, which one makes sense. The other thing I'd like to say is because the bandwidth continues to increase, the equalizer and equivalence become even more important, because you don't want a wide range of levels coming into your end device or your cable modem / gateway. That definitely makes it harder to operate correctly when you have a wide range. So these conditioners give us the perfect opportunity to flatten that signal out and make sure we have a good flat signal. And thirdly, as we start migrating to single outlet homes, you may see some fairly low levels at taps, when you go there, but keep in mind, 2 dB is kind of the equivalent of what used to be a 10 dB because you were overcoming splitter loss. So now that these drops are kind of home runs, you're not going to need a lot of signal at the tap on the downstream. And certainly the echo cancellation becomes very important because you got a small signal coming down into the 4.0 modem gateway and just a whole lot of power coming back out. So kind of changes things around from my days in the business. So something we need to pay attention to. And I'm looking for any additional questions. Does anybody have any questions they would like to ask Neil? Okay, Neil, I do not see any, but I would just want to take a moment to thank everybody for joining. I think this was I do have one more question. I'm sorry. I hope
Okay.
this provides benefit to everyone, or hope the questions I asked this morning provide benefits for everyone. So as we increase the bandwidth going through the devices, passives, and taps, does that increase any or stress the circuitry in there any more than it used to? I mean, used to we were fairly simple, low bandwidth, 5 to 42 on the return, and say 750 or 860 on the forward. So you have to keep the AC and RF circuitry separated, and then you have to have obviously port-to-port isolation. But say an older device, is it going to be able to handle that, or is it going to run into some problems with the additional bandwidth?
Yeah, so those are things we continually test, and as we know, there is a higher composite power coming out of the devices at the node and at the modem. So we're used to transmitting in the upstream from 5 to 42. Now we're transmitting, up to 684. And that extra loading has some impact in terms of how linear the passive is. So passives are able to do splitting and directional coupling and splitting your signal through what we call ferrite devices inside the tap. And these are splitters and couplers that actually divide and separate your signal. Those do have will be affected by power level. So the higher the power level, there is distortion that can come out of ferrites. So all of our products are designed to maintain the distortion levels that are expected. The good thing about some of the next generation full duplex, DOCSIS 4.0, they have a lot of mitigation through digital signal processing techniques to mitigate and to remove a lot of these impairments. So yes, putting more signal and higher power levels through a device that is older may have some distortion impacts, but FDX is designed purposely to not needing to replace your passives. So there are digital signal processing that helps remove those impairments from distortion within the FDX DOCSIS modem itself. Good question. But yes, ferrites do need to be linear, and that's something that is always, all the vendors do ensure linearity of those ferrites for the proper network loading.
And finally, I think, an interesting note, I noticed when I would put taps or passives on the bench and sweep them low frequencies, I kept seeing attenuation go higher at the lower frequencies, and I go, why is it going higher? And I asked a few people, and then of course I get a hold of my longtime acquaintance Ron Rannick, and he says, oh, because you're getting closer to the AC choke. So AC chokes, when you get down below 5 megahertz, start to have an impact. So you actually have some more loss at that lower end, which kind of helps with some of the ingress, because it will the RF chokes the AC chokes will attenuate some of that low ingress, maybe below where you're looking, which helps with some of the interference. But that was a surprise to me. I didn't realize, oh, okay. Getting lower doesn't mean necessarily always less attenuation because of the AC chokes.
Correct. I mean, we were so used to talking about 5 megahertz on up, but a tap really, legacy taps really have 3 frequency bands. You have your upstream and downstream. So upstream starts at 5, but there's another diplex that you don't realize, which is 60 hertz, which is the AC choke. So there are 3 frequency bands, the AC that goes through that tap as well as the RF. And that is separated by that AC choke. And it's really a diplex as well.
Yeah, that's very true. So I found that very interesting. Well, we will call it the end now. So I just want to thank everybody for joining, and a special thanks to Neil for presenting. I learned a lot, and I hope everybody else did too. Thank you, Neil.
Thanks. Pleasure to help everybody here. Thank you.
Okay. Have a good day, everybody.
Take care.